Okay, here's our problem. We have a tank, and it is well insulated. And this tank has a vacuum in it. Okay, and the volume is equal to 10 liters. Okay, so that's what it is. A tank that has a vacuum, 10 liters. And what's going to happen is it's going to develop a little hole in the side of it, and we're going to have air rushing into this tank. Okay, so what happens is the surroundings is 1 bar and 25 degrees Celsius. And this tank is going to fill up. This vacuum is going to fill up until we have equilibrium happening, so that the pressure is equal inside and outside of that tank. Okay. Now this is obviously a transient problem, and how do we note it? Because there's an inlet, but no exit. If this is my control volume, there's an inlet but no exit. So of course it has to be transient. Okay, and so that's what I'm going to tell you right now for your problems in this class. You will be able to denote a transient problem if it has an inlet but no exit, or an exit but no inlet. That is where we're going to be focusing our efforts and trying to understand this material on. Now, of course, you can have a transient problem that has more exiting than coming in, or more coming in than going out. That's also a transient problem. But we're going to simplify and only look at 2 types. Inlet with no exit, exit with no inlet. Okay, so let's take our equations that we have derived from earlier, and we're going to have this. We're going to have the mass of the control volume at state 2 minus the mass of the control volume at state 1 is equal to mass in minus mass exiting. And we have the internal energy of my control volume at state 2 minus the internal energy of my control volume at state 1 is equal to Q minus W plus mass in, enthalpy in, minus mass exiting, enthalpy exiting. Those are the 2 equations that we have worked with. Always our first step. Now we're going to simplify here. Well, what can we simplify in this equation? We know that there is no mass in the control volume at state 1. It was a vacuum. So this goes away. We also know there's no mass exiting. So this goes away. All right? So this says the mass of the control volume at state 2 is equal to the mass coming in. That makes sense. Makes total sense because there's nothing in there before. We're just sucking air in. That's what's going to happen. Let's look at the second law, or sorry, the second equation here. The internal energy of the control volume at state 2 minus the internal energy of the control volume at state 1. Well, there isn't anything in the control volume at state 1, so this is going to go away. We're also told that there is no heat transfer, because as they said, it's insulated. And we don't see anything inside of here that's creating any power, so there was or any work, doing any work, so the W goes away. And we have nothing exiting, so this goes away. All right, we have simplified these equations significantly because of how we're working through it. So we're going to have mass of the control volume at state 2 is equal to mass coming in. And then we're going to have internal energy of the control volume at state 2 is going to be equal to mass in, enthalpy in. That is the next step we do. First, we integrate our equations. Second step is that we simplify our equations with all our assumptions or knowns. The third thing we do is we're going to take these 2 equations and combine these 2 equations. So now we're going to combine. Okay, and so let's look at this. This equation, how do we combine it? Well, we can say, I can just replace this in here and say that the internal energy of the control volume at state 2 is equal to mass of the control volume at state 2 times enthalpy in. Okay, now we have to also remember that this, what is this here? This internal energy, this is going to be equal to mass of the control volume at state 2 times specific internal energy of the control volume at state 2 is equal to mass of the control volume at state 2 times enthalpy in. Okay, I'm writing that big U as a lowercase u because we're talking about mass times the specific internal energy. And look what happens there. Now we're saying that this and this will cancel out. And for our problem, it's very simple here that the internal energy of the control volume at state 2 is going to be equal to the enthalpy in. Okay? Now there's two ways to solve this problem from right now. And it's going to involve, we can look in our charts. Because we know this enthalpy coming in, is at 1 bar and 25 degrees Celsius. Okay? We could go find that value and see where we have an internal energy that matches that point. And from there, we could figure out what is the final temperature, for example. If we're looking for the final temperature. What are we looking for in this problem, to be quite honest? Final temperature. We're looking for the final temperature. So we could look up 1 bar, 25 degrees Celsius, and say, okay, that's what the internal energy has to be, and then go down our tables and find out where that is equal to. That is a nice way to do that problem. And if we did that, we would not be perfect here. It would be there would be some interpolation that needs to happen. And I've done this one already, and I get the answer is 416.43 Kelvin. That's what we get if we look at the tables. Okay. Now, what I want to do is I want to show you what would happen if we were to assume something differently. Let's say we were to assume that in this problem statement, we were to assume they told us ideal gas with K is equal to 1.4. Okay, now that changes things, because once they tell us K is equal to 1.4, now they're telling us don't use the variable specific heat method, that is the tables, but use a constant specific heat method. Okay, so this is going to be a little bit more algebraic that we have to work with. And this is not as straightforward as the tables. Even though you have to do integration, it's just not as easy. Okay, so the first thing we would do here is we would say this. The internal energy at state 2 would be equal to, well, I can rewrite enthalpy as internal energy in plus pressure times specific volume in. Okay, and I could write this as pressure in specific volume in. Okay, now I'm expanding how we define enthalpy. We are going to very rarely do this. Okay, this is a very interesting case that we're going to do this on. Okay, and we also know that for ideal gas, that PV is equal to RT. Okay, so I could rewrite this as U2 is equal to UN plus R times temperature in. Okay, and what I can do here is now rewrite this as U2 minus UN is equal to RT. And that's really what I want to do. I want to get something where I have a delta U, remember, because when I'm doing those constant specific heat methods, I know that I have C sub P delta T, C sub V delta T. I have to have that there's a delta U that equals those things. Okay, and so that works for us now, because now this can be equal to C sub V times T2 minus Tn is equal to R Tn. Okay, and that's good because I'm looking for this T2. This is what I'm looking for, this T2. Okay, now C sub V. When I'm given a K value in the problem statement, I have to calculate my C sub V. That's what it's asking me to do. And I know that C sub V is equal to R all over K minus 1 times T2 minus Tn is equal to R times Tn. And now I see there's an R on both sides of the equation, which cancels out. And I can simplify this as T2 minus Tn is equal to Tn times K minus 1. Okay? Now here's where I'm going to stop. I'm going to stop it right here, because I've done the bulk amount of the work, the algebra, the what I would consider the really tricky parts of this problem. I want you to sit down and say, okay, what is the temperature? In fact, no, I'm gonna find the temperature for you. I'll have you do something else. I'll find the temperature here. I'm trying to think ahead of the game what I want to do here. So let's do this here. Temperature 2 minus temperature in is equal to temperature in times K minus temperature in. Okay? Now look what happens here. If we add a temperature in to both sides, this is going to cancel. And we're going to get the very simple equation that T2 is equal to Tn times K. Well, that's really a straightforward thing. We know that our temperature in, they told me the temperature in was what? They told me, if I go back to my notes, it was 20 degrees. 25 degrees Celsius. So T2 is going to be equal to 25 plus 273. Remember, we have to convert everything we're dealing with ideal gas into absolute temperatures. Okay, I didn't want to. I was worried that maybe if I gave this to you as a lecture problem, you would forget that 273. Okay, and we would take this times K value, and this is a capital K, so I don't want to convert. Times the K value, which is 1.4. And if I got the answer, T2 would be equal to 417.41 kelvins. Okay, that's very similar to what if I were going to do a problem that was variable specific heat, when I got 416 Kelvin. Okay, now that's hot. You think, why is it so hot? Okay, why is the temperature rise when I'm just trying to equalize that? Well, that flow in is doing a lot of stuff. It's the molecules are getting more excited. There's going to be more internal energy that's going to be happening there, and it makes sense that the temperature should rise. It's not going to be the temperature is going to be equilibrium, and you've seen this before, kind of in an opposite way, in a way that we'll probably do a problem with. Have you ever had a can of air? Maybe you had some air cleaner that cleans off the keyboard. Shoots out clean air, or you've had an air horn and you've pressed the button on the air horn, and or any type of cleaner that's in a container where you have a spray bottle, maybe just like a paint can. What happens to the paint can? You notice is as that air is leaving, that can starts to get cooler to you. Same thing will happen as air enters that. The air will get hotter. So it's something that you probably experienced. Now you just have to kind of understand it in now a thermodynamic way. Okay, here's the next problem, and here's where I'm going to ask you to do for the lecture quiz problem. I want to know how much mass enters. How much mass enters that tank to get equilibrium? Okay, now, when you think about mass and you think about ideal gas, you should think PV is equal to mRT. Okay? Now, when we're looking at mass enters, we have to look at that final state. So this has to be P2, V2, M2, R2, T2. And so we can solve this to say the mass is equal to P2, V2 all over RT2. Okay, so now we know what our T2 is. I want to use this temperature 2. This is going to be our temperature 2. We know our pressure 2 is going to be 1 bar. We know our volume 2 is going to be, what did I say it was? 10 liters? 10 liters. And we know what R is. We can calculate R. This is good practice for your exam. There's going to be some conversions here from bars. There's going to be volume, which is in liters. There's going to be R value that you have to work with. Find out what the mass is, and I want what the mass is in grams. Okay, not kilograms, in grams, because your mass is going to be very, very small. It's going to be in the grams. So please enter what it is in grams into the lecture quiz portion of this, and that will be where we'll be ending today. This portion, or this example problem.